Right. Yep. What time do you leave? Yeah.
Do I what?
Do you have a class before this or no?
Not before this, but I have classes after this. Yeah, my Mondays and Wednesdays are long. I teach until 8:30 on Mondays and Wednesdays. Because all our graduate courses are in the evening, so that's when I teach them.
So this is your first one?
Yep, it's my first one today.
I hate my Thursdays.
Oh, eh? Well, how come?
I have a lab in the mornings. We're 16. I have a break. And I have econ. I have another break.
Oh, wow, that's a lot.
At least I live close, I go home.
It's a long day. It's a long day though.
Oh, Mondays and Wednesdays are long.
Oh, wow. That is a long day. I was gonna say, I was gonna complain that I have to get here at 8:30, just even on Mondays and Wednesdays, just to get parking, and then I still say 8:30, but I definitely don't get up at 4:30 in the morning. I see. Hey, how's it going?
Like a. I'll tell you what. I'll be better tomorrow. Yeah. I just have a comment. Yeah. It's a very situation.
Yeah, but for all the data. Yeah. Yeah. But you don't get the pressure. You- Right? And you look at it, all this value compared to everything else. So I'm all being so. That's what it brings up. So we're thinking about what I bring up. Oh, we got to.
All right, it's 2:30, so let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? Doing good, doing good. All right, end of week 8. And so one more week and then we have spring break. So that'll be exciting. All right, so I do have a few more exams here. And so if you didn't get a chance to pick up your exam on Monday, I have them here for you, okay? And if you're not able to come to class today and you want to see the feedback on your exam, you can just email me and let me know. And I can scan your exam for you, okay? Or if you don't want to see your exam, that's fine too. You know, I'm not forcing you to look at the exam, but you know, but I do think the comments should be helpful. You know, especially, you know, I think especially for when you're studying for the final exam, because the final exam in this class, it is going to be cumulative. And so you are going to need the stuff here from the first midterm, you know, to help you study for the final. And so I think generally people find those comments and seeing their work, you know, kind of helps for that. And so, you know, just from those perspectives, I think it would be good to look at your exam. Yeah. Yes, yeah. So for the final exam, you'll be allowed 2 sheets front and back. Yeah, but we'll talk a lot more about the final later. Because it's even though it's cumulative, it's not going to be absolutely everything in the class. So I think that's way too much. It's kind of more sprinkled throughout, but usually my policy for the final exam is, you know, the semesters we have 15 weeks of instruction. And so I try to limit the final exam to be like 10, 11 weeks of content. So I try to shave off like, you know, about 4 or 5 weeks of content for you to study. One more announcement. So there was some errors in my solutions for homework 4. Okay. And so if you've already started homework 4, you probably have noticed that you're getting different answers on problems 2 and 3. And so I've updated the solutions to fix that. Okay. Okay, so if you haven't started yet, don't worry about it. I've already updated the PDF with the correct solutions, but if you've already started, make sure you download the updated PDF. Because I messed up the everything with the mixed boundary layer stuff. Okay. And so make sure you download the new PDF so that you can get those updated solutions. Okay. All right, and so I think that's all my announcements. So are there any questions I can answer before we get started today? Okay. All right, so let's go ahead and pick up where we left off. And so the last thing that we covered, let me just scroll up a little bit here, is this, and don't worry about this down here, is this what I call the convection problem solving recipe. Okay. And so a lot of convection problems will kind of break down into these 5 separate steps. Okay? So the first thing you're going to do is you're going to identify the geometry. Next, you're going to compute the film temperature, where remember the film temperature is the temperature at which you're going to evaluate the fluid properties. Okay? 3, you're going to compute the Reynolds number, and then you're going to use that Reynolds number to inside the Nusselt correlation. Okay? And then you're going to use that Nusselt correlation to compute convection coefficients and all that good stuff. Okay. And so this should be, from the end of the notes last time. And so, I don't want to write it again, but what I do want to do is I want to jump into an example which kind of shows this process in action. Okay. All right. So let's go ahead and jump right into it then. Okay. So I like this example a lot. It's one of my more favorite examples in the class because I think it's pretty practical. And I haven't done this before, but I do aspire to do this one day. This could help you in designing your own rig. And so if you're interested in PC gaming like I am, probably one thing that you've thought about at some point is designing your own PC. And part of that is designing the cooling system for that PC. Okay. And so we're going to be designing that in this problem. And in particular, we're going to be worried about the design of the fan that's going to blow air over our fin. Okay. Okay. And so this fin, might be something, it might be a thermal sink that you use on your computer in order to cool it. Okay. And anytime you build a computer, you have to have some kind of air cooling that, or some use water as well, okay, to cool your parts. And so what we're interested in this problem is, we're interested in computing how fast of the air or the air velocity that we need in order to properly cool our part. Okay? And so the velocity here is going to be unknown. What we do know is that the air temperature is going to be a cool 20 degrees C. Right. And what this is going to be cooling is it's, the only geometry that we can do so far is a flat plate. Okay. And so this flat plate is going to represent some kind of fin, and it's going to be at a constant surface temperature Ts. Okay. Where the surface temperature of this fin is going to be 45 degrees C. Okay. And so let me give you some geometric properties. And so the length of the fin is going to be 10 centimeters. Okay. And the width, the width of the fin going into the page, and so we assume that it's a rectangular plate, is going to be 5 centimeters. Okay. Not only that, we also know the amount of power being generated by the computer. Okay. And that power needs to be dissipated in the form of heat. Okay. And so one way we can model that is we can say that the Q coming in is going to be equal to 5 watts. Okay. All right. And so we're interested in this situation, and more specifically, we're interested in seeing, how fast does the air need to go to offload that 5 watts of heat. Okay. Oh. It's going to be the amount of air velocity we need to offload that 5 watts, but also to maintain that surface temperature of 45 degrees C. Okay. All right. And so it's a little bit, it's not as direct as some of the previous problems that we've been doing, okay, because we're solving for velocity here. But what this is essentially is solving for, or what we're essentially looking for, is what does the convection coefficient have to be, in order for this situation to work out. Okay. All right, and so it may not be as direct as before, but this fits into our category of our convection problem solving, and so we can apply the convection problem solving recipe in order to solve. Okay. All right, any questions with the problem setup? Okay. All right, so let's start with the recipe then. All right, so step one of the recipe. Step one of the recipe is to identify our geometry. Okay. Again, this is probably the most skipped step in this entire process, but I do want you to actually write this down. Okay. Here it's a little bit obvious just because we've only gone over one geometry so far, but it's always good to write it down. Okay. And so our geometry in this case is one of a flat plate. Okay. Right. And so you can identify that from the figure of the problem. Okay. All right. So the next thing we're going to compute is the film temperature. Okay. And so the film temperature, remember the formula for that is it's going to be the average between whatever our surface temperature is and our fluid temperature. Okay. So our surface temperature here is 45. Okay. Our fluid temperature here is 20 degrees C. Okay. And we're going to divide this by 2. Okay. And we get a film temperature of 32.5 degrees C. And so that's the average fluid temperature, in between the free stream and the plate. All right, and so the next step is we're going to evaluate the air properties at this temperature. And so you can do that a couple of different ways. And so if you have the textbook, you can go to table A4, which is in the back of the book, right? Or you can use the online fluids calculator, which I showed you last time. Oh, I put a link to that fluids calculator on the homepage of our course website too. And so you can go click the link there. Okay. And so if you compute those or look those up, you end up with the kinematic viscosity of 15.89 times 10 to the minus 6 meters squared per second. Okay. We get thermal conductivity of 26.3 times 10 to the minus 3 watts per meter Kelvin. And you get a Prandtl number of 0.707. Okay. Right. All right. So that's great. And so, now that we have the fluid properties, we can move on to the next step. Okay. And the next step is to compute the Reynolds number. Okay. So remember the formula for the Reynolds number is U infinity multiplied by the length divided by nu. Okay. And so here's where this problem is going to be a little bit different, because usually at this point, you'll have everything that you need to plug in to find the Reynolds number. Okay. But for this problem, we don't have everything, because what we're solving for is U infinity, and we of course we don't have that because we're solving for this yet. Okay? And so we can't solve for this yet. And that kind of presents a little bit of a problem for us because, you know, at this point, we have to make a decision on whether our boundary layer is going to be laminar or turbulent. But without the Reynolds number, we can't really make that determination, at least, you know, not definitively. Okay. And so at this point, we're going to make an assumption. And so, you know, just because it's a little bit easier to deal with, we're going to assume that it's laminar. Okay. And then later on, once we do solve the velocity, we're going to go back and verify that it's actually laminar. Okay. And so if you ever run into a situation like this where you have to make an assumption of whether it's laminar or turbulent, you know, a lot of times it's good to look at just kind of take a step back and look at your physical situation, okay? And so our physical situation here is, you know, we basically have the flow of air inside a computer, okay? So it's a fairly confined space, and those fans, you know, these aren't kind of like those mega omega fans that you find in like a Dyson vacuum fan, right? It's just one of those little, you know, dinky fans that are blowing air. And so those things can't really blow air super fast. And so, you know, based on those situations, based on the fact that our space is relatively confined and our velocities are probably going to be relatively low, you know, the laminar assumption is pretty, you know, it's pretty reasonable here. Okay. In fact, I'd be pretty surprised if you ever get the flow to be turbulent in such a small space. So we'll assume laminar for now, but of course, you know, we'll go back and verify it later. Okay, so let me pause here. So are there any questions on this so far? Yeah. It depends on the situation, but for a lot of the problems and for the homework problems especially, you'll have the velocity already, actually. And so at this point in the problem, you know, if you have the velocity, if you have the lengths, and you'll have the viscosity too, you can just compute outright what the Reynolds number is. But for the situations where you do have to make an assumption, you know, just kind of look at the situation. And so if you're looking at, you know, let's take another extreme. So let's say that you're looking at airflow over an airplane. And so the airplane's going really fast and it's really big. And so in that situation, I would say it's most likely going to be turbulent. And so, you know, the assumption of turbulence will be good in that case. Yeah, but most of the time you won't have to make this assumption, but we're going to do that here for this problem. Okay, so let's go on to the next step. Okay, so the next step is we have to make a determination whether we want a local Nusselt number or an average one. Okay. Okay. And so, you know, like I said last time, most of the time for most of these problems, you're going to want an average Nusselt number. Okay. Just because the nature of the problems that we're looking at in this class, we're looking kind of at systems as a whole, okay? And so, you know, if we go back up to this problem, you know, what we're interested in is kind of the heat loss from this fin as an entire system, okay? And so in situations like this, when you're interested in, you know, systems as a whole, you know, most of the time you're going to want the average Nusselt number, which is going to give you the average convection coefficient. Of course, there are situations where you want the local one, but you know, for analytical methods like this, you know, that's pretty rare, I would say. So, you know, most of the time you're going to want the average. Okay? And that's important because, you know, remember there's different Nusselt number correlations whether you're working with the local or the average Nusselt number. All right, so with all that information in mind, now that we know that or at least we're assuming that the flow is laminar and we want the average Nusselt number, we can go ahead and select the appropriate Nusselt correlation. Okay? All right. Because remember, you know, there's lots of different formulas out there for the Nusselt number. So you have to pick the right one for the situation. Okay? And so for this particular problem, we have laminar flow. Okay. We want the average one. and our geometry is one of a flat plate. Okay. And so we look at our list of all the neutral number correlations that we have, and we use the following one. Okay. And so our appropriate neutral number correlation here is 0.664 times Reynolds number to the 1/2 power times Prandtl number to the 1/3. Okay. So this is the correlation that corresponds to all of these conditions here. Okay. Right. And if we go off the definition of the neutral number, it's the definition of the neutral number is the convection coefficient multiplied by the length divided by the thermal conductivity. Okay. All right. And so here, we've made some good progress towards the result, but we still have a bit of work to do, because remember, we don't know what the Reynolds number is yet, and so we can't plug in for this formula outright. But what we can do is we can use this expression here along with some other information we know from the problem to eventually compute that velocity. Okay. And so to kind of show that, let me go ahead and plug in for the Reynolds number here. Okay. Listen. Okay. And so if I plug in the expression for the Reynolds number, we see that the Reynolds number is U infinity times L divided by nu. Okay. Right. We can see here that we finally have an expression where we can solve for U infinity, right? Because remember, U infinity was our unknown. And so let's take this expression and solve it for U infinity. All right, so let me go ahead and divide both sides by 0.664 and the Prandtl number. Okay, and so what we have is U infinity times L divided by nu to the 1/2 power is equal to H bar L divided by 0.664 Prandtl number to the 1/3 times thermal conductivity. Okay. So let's square it. And so if we square it, we get U infinity times L divided by nu is equal to quantity H bar over H bar L times 0.664 Prandtl number to the 1/3 times Kf squared. Okay. And so let's go ahead and isolate U infinity. And so let's multiply both sides by nu and divide by L. And so in the end, what we get is U infinity is equal to nu divided by L times H bar L divided by 0.664 Prandtl number to the 1/3 Kf squared. Okay. And of course, you have an L squared on top and an L on the bottom, so you can cancel that if you want. But I'm just going to go ahead and leave it in this form. Okay. And so what we've done so far is that we've taken, now that we know what neutral number correlation applies to this problem, we just use that correlation to solve for the unknown velocity. Okay. And a lot of these quantities we can plug in. Okay. And so, the kinematic viscosity we can plug in because we solve for that in step 2. The length we know from the problem, the Prandtl number, and the thermal conductivity we also know from step 2. Okay. But the big elephant in the room, and the one that we don't know yet, is H bar. Okay. And so in order to properly solve for this problem, we need to solve for a value for H bar. Except spelling is hard. Okay. Okay. And so we're going to have to come up with a way to compute the convection coefficient based on the information that we have in the problem. Okay. And so if we can do that, if we can take the information that we have in the problem and use that to compute H, then we can just plug that in here and eventually solve for U infinity. All right, any questions on this so far? Okay. All right, so let's scroll back up here and look at the problem. Okay. And so what do we know from the problem? So we know that the fin is going to have a surface temperature of 45 degrees C, right? We know that the air surrounding it is going to have a temperature of 20 degrees C, right? But we also have one other piece of information, and I kind of glossed over it really quickly, but that piece of information will actually be key in computing H, okay? And that piece of information is the amount of power that's being generated by the computer, okay? So usually we don't have that, right? So remember, for most of these problems, what we're given usually is the surface temperature, and we're given T infinity. And then based on those two, and also on the convection coefficient, we have to compute Q, right? In this problem, I kind of threw you a little bit of a curveball and said, let me give you Q instead, and you can use that information however you want, okay? And so since we have Q, we have TS, and we have T infinity, we actually have almost everything we need to plug into Newton's law of cooling, right? Okay. And so what does Newton's law of cooling say? So Newton's law of cooling says that the heat transfer due to convection is equal to H times A times the difference in temperature between the surface and the fluid, right? Okay. Let's go through each term in this expression here and look at, well, which ones that we know. All right, so let's start with TS. And so TS, we obviously have that. And so we know TS is 45 degrees C. I lost it already. It's 45, right? Yeah, 45. So we know TS is 45 degrees C, okay? We know T infinity, that's the fluid temperature, so that's 20 degrees C. Okay. Q, we actually also know as well, okay? It's phrased a little bit differently, right? And so remember, the problem phrases Q as the power that's generated by the computer, right? But that power has to go somewhere. It can't just go into the abyss, right? And so what we're basically saying in this problem is that all the power that's being produced by the computer, it's coming out through the fin, okay? And the only way that heat can come out from the fin is through convection, right? And so we actually already have this one as well. And so the Q convection here is going to be the 5 watts that's generated by the computer. Okay? Okay. And we also know the area as well. And so the area is just going to be the length, because we have a rectangular plate, it's just going to be the length of the plate multiplied the width by the width of the page. Okay, so L times W. Okay. Right, and so now that we have an expression here where we know everything except for one thing, that means we can use this equation to solve for that one missing thing. Okay? And so let's solve this equation for H. Okay? And so what we get is H is equal to Q divided by L times W times TS minus T infinity. Okay. Right, and in fact, this H that we compute here, this is the H that encompasses the entire fin. And so this is exactly the H bar that we're looking for. And so we can take this H bar, plug it in back up here, okay? And once we plug in that H bar up there, we'll have everything that we need on that side of the equation, okay? Okay, and so now that we know H bar, and we know everything else here in this formula for U infinity, we can plug it all in and solve for the velocity. Okay. Okay, so it's a lot of plugging in. It's a lot of numbers, and so I'm not going to go through the whole thing. Okay. And what we get is a U infinity of around 10.5 meters per second. And so the fan that you buy for your computer has to have a speed, or the speed of the fan has to be fast enough to at least produce a 10.5 meters per second wind speed. Okay. And so if you can buy a fan that does that, then your computer will be optimally cool and you can game as much as you want. All right. So one last thing I want to check for this problem. Remember, the key step that we made here is we had to assume that the flow was laminar. And so let's just check to make sure that that's the case. Okay. And so if we plug in, so we have the Reynolds number is equal to U infinity multiplied by L divided by the kinematic viscosity. Okay. You plug all that in, we get a Reynolds number of 6.61 times 10 to the 4th. Okay. And if you recall from last time, the critical Reynolds number for external flow like this is 5 times 10 to the 5th. Okay. And so since we're less than that, and since we're only 10 times 10 to the 4th, we're good here. And so this flow is confirmed to be laminar. All right. So that was quite an involved example. And so that was, but I wanted to make sure I go through it slowly and kind of through every step because, I think this is a cool one. And so it's, maybe not the most straightforward application of the recipe because we kind of had to do a couple additional steps. But I think it's a good demonstration of, of what these problems can be like. All right. Any questions on this example? Okay. All right, and so that's going to do it for the flat plate, and so we're basically done with that flat plate geometry. And so now let's start introducing some other flow geometries into our mix. Okay? And one that's really important, I think, for the design of a lot of systems is the so-called cylinder and cross flow. Okay. All right. And so the important thing I want to note, because people get confused about this every single year, right? So the next unit that we're going to go over after this is internal flow. And so one of the more common situations for internal flow is flow through a cylindrical pipe. Okay? That's flow inside a pipe. This cylinder and cross flow is flow outside a pipe. Okay? And so think about a pipe that's kind of sitting on the outside, say it's on the top of the building, right? You have wind that's going to flow over the pipe, okay? And so you have convection that's going to occur on the outside. So that's the situation that we're looking at. And so for the flow of water, inside a pipe, we'll do that, maybe at the end of today if we have time, but definitely next week. All right, and so the situation looks like this. And so here we have our cylinder. Okay. Our cylinder has a certain diameter. We have flow, okay? It's going to be hitting the pipe from the outside. And what's interesting about this, more so than the flat plate, is that the velocity will kind of, have to go around the cylinder, okay? And so you get streamlines that kind of look like this. So I like to go over this one because, if you work in any kind of, system that uses any kind of pipes, how you insulate the outside of those pipes, from air and the weather and stuff, that's an important design consideration. And so, besides the flat plate, I think this is kind of an important one for us to do. Okay. All right. So what's unique about this geometry? Okay. And so relative to the flat plate, of course, we're going to have different flow patterns. And so since we have different flow patterns, of course, that means our Reynolds number correlations are going to be different. Okay. And so we're going to have, you know, different ways to compute the Reynolds number. And one of the principal ways that the flow patterns are different is we're going to have a new phenomenon known as separation. Okay? Did you guys talk about boundary layer separation in your fluids classes before this? Yes, no, mostly you've heard the term before. Okay, so that's good. Okay. And so if you're curious, you know, you probably heard of stall in an airplane, right? So stall is when you kind of go up and your plane just stalls and you fall out of the air, and it's a terrible thing. And so one of the reasons stall occurs is because you have a boundary layer that separates from your plane. Okay. And so if you're interested in aerodynamics at all, then boundary layer separation is something that you're going to be, you know, studying a lot. Okay. But we're going to talk about just the kind of the thermal effects of separation here. Okay. And so I think the easiest way to kind of illustrate this is with the picture. Okay, so let me go ahead and draw our cylinder again. Okay. And we have flow that's coming at it. Okay. And just like the flat plate, you know, whenever you have flow that's kind of striking a surface or kind of moving past a surface, you're going to have a boundary layer that forms. Okay. So let me draw the boundary layer with a different color here, just to make it clear. Okay. Remember, the boundary layer is this thin kind of layer of fluid that kind of acts as a transition between the solid surface and the fluid. Okay. So here is our boundary layer. Normally what we expect from the boundary layer, you know, in the flat plate, remember the boundary layer, it kind of always stayed attached to the surface, right? And so there's always kind of this thin film of fluid that kind of always stayed attached to our flat plate. Okay? Because of the geometry of the cylinder, okay, most notably kind of around this area right here, okay? So I stopped the boundary layer here on purpose, okay? It's not perfect, but imagine that's kind of the symmetric place on both, okay? The fluid kind of has to make like an inward turn here, okay? And so if you compare kind of the front end of the cylinder compared to the back, right? It's kind of easy for the fluid to go around the front because the fluid is kind of always kind of colliding with the surface, right? And so the fluid wants to go from left to right, but as it goes from left to right, it collides with this surface, okay? And then it's forced to turn to go around, okay? But once the fluid kind of makes it over the top, you know, there's nothing really forcing it to stick to the surface, okay? And so you kind of have a fundamental difference. And then, you know, if you're going to ask the fluid to turn this way, right, to turn to kind of be with the cylinder more, it doesn't really want to do that because ultimately the flow wants to go from left to right, okay? And once it gets past the top of the cylinder, you know, nothing's really getting in its way anymore, okay? And so instead of staying attached to the cylinder, what tends to happen is that the fluid just kind of continues on like that. And it's at this point when the boundary layer kind of, you know, leaves the surface. This is what we call boundary layer separation. And then after the boundary layer separates, it creates a region on the back of the object known as the wake. And so you probably this is something you're familiar with. And so if you've ever looked at a boat kind of sailing through the water, right, there's always that region behind the boat, you know, and because of the way the boats are designed, it kind of, the wake kind of keeps growing in a cone like that, okay? And so that wake that forms is a direct result of boundary layer separation. Okay? And so why am I bringing that up, right? Because this is a heat transfer class. And so why do we care so much about these fluid mechanics? Well, the fluid mechanics in the wake are very, very different. Okay? And I'll try my best to kind of illustrate that here. Okay. And so if you compare the flow situation kind of before the cylinder and the wake, what you have is that in the wake, you have flow that's kind of circulating. It's kind of slow. It's kind of, it's a little bit chaotic. It's not quite turbulent, but it is a little bit more chaotic than before. Okay. And so you have a little bit more vortexes that form. You have a little bit more whirlpools that form inside this region. Right? Compared to upstream, maybe you have just kind of uniform velocity patterns. Okay? And what do we know about when the flow turns chaotic? We know that when the flow turns chaotic, this actually enhances heat transfer. Okay, and so convection is enhanced in the wake. And so from that perspective, it's important to know. Okay. And so the amount of convection that we have, it's going to change depending on how big our wake region is going to be. Okay. All right. Any questions on this? Okay. All right. So the situation I've shown you here, this is for laminar flow. Okay. Let me write that in blue. And so when you have laminar flow, the flow separates kind of at the tops and bottoms of the cylinder, approximately. It actually happens a little bit before that, but for all intents and purposes, let's say that it occurs at a 90-degree angle. Okay. Okay. And so basically, once the flow tries to make that turn, it just can't do it anymore. Okay. Let's sketch what the situation looks like for turbulent flow. And so whether the flow is laminar or turbulent, it is going to change the location of separation. Okay, so turbulent flow separates at a different point, but the question is, is the flow going to separate before the 90-degree point, or is it going to separate after? What do you guys think? Do you guys think it's going to be before or after? Before, okay. Any after takers? After, okay. So let me so let's do it like this. So when you have turbulent flow. Turbulent flow, even though it's more chaotic, ultimately its Reynolds number is higher. And so one thing that you can say is that turbulent flow has a lot more kinetic energy because it's just naturally faster. Okay? Okay. And what that kinetic energy allows it to do is that it allows the flow to do some maneuvers that it couldn't do elsewhere. Okay. Another way that you can look at boundary layer separation is that it takes some energy for the flow to kind of make this turn, right? Because ultimately, what the flow wants to do is that it wants to keep on its course, going from left to right, right? But once it hits the cylinder, it's like, I have to make a turn because the cylinder is making me do it, right? But once it reaches a point where it doesn't have to turn anymore, he's like, all right, I'm out of here, and so it just kind of forms a wake. Okay? Turbulent flow, on the other hand, has a lot more energy. And so what that allows it to do is that it allows it to kind of maintain the boundary layer for a little bit longer. Okay. And so what you see for turbulent flow is that the boundary layer actually separates after. Okay. Okay. And if the boundary layer separates later, this results in a smaller wake. Okay. And so if you have a cylinder or any kind of blunt object, really, and so a lot of this flow, a lot of the fluid mechanics that we're talking about here, applies to any kind of, we call it a blunt object. Okay, that's the opposite of an aerodynamic object. Okay, so the opposite of a Lamborghini. So think of like that weird Cybertruck that Tesla has or something like that. Okay, and so you have a smaller wake. Okay, but even though the wake is smaller for turbulent flow, you're still going to get enhanced heat transfer if you have turbulent flow. Okay. I should say overall. Okay. And so even though we know the wake enhances the heat transfer, and so you would think that if you have a smaller wake, you're going to have less heat transfer. But the effects of turbulence are just so strong that it kind of overcomes that wake. But because of that, we have a few competing factors here. The relationship is not exactly as straightforward. So it's going to be a little bit different than our flat plate case, where for the flat plate, we had one correlation for laminar, one for turbulent. Here we have to do it in kind of different regimes because of the wake is changing size, but the boundary layer is also changing characteristics, and so it's a little bit more complicated situation. And so we have a more complicated Nusselt correlation as a result. Okay. All right. So any questions on any of this? Okay. This is all just pure fluid mechanics, and so I always love talking about fluids. Okay, and so with all that in mind, so now that we have an idea of what the fluid mechanics look like, that'll motivate our formula for the Nusselt number. Okay, and so for a cylinder and cross flow, okay, our average Nusselt number takes the following form. All right, so our average Nusselt number is going to be C multiplied by the Reynolds number with respect to the diameter raised to the m power times Prandtl number to 1/3. Okay. And so there's a few things I need to point out with this equation. So let's kind of take them one at a time. So first thing is the Reynolds number. And so the Reynolds number in this case, I made the slight note there that it's the Reynolds number defined with respect to the diameter. Okay. And so that means when we compute it, the way we compute it is we use the diameter of the pipe. Okay. So we have U infinity times D divided by nu. Okay. So that's a little bit different because we don't have the length of the pipe anymore or the length of the plate. We actually just use the diameter of the cylinder. Okay. All right, and so that's the Reynolds number. And so now we have the constants C and M. Okay, and so the values of C and M depend on what the Reynolds number is. Okay, and it's a little bit more of a complicated case in our flat plate. Okay, and so what we say is that if the Reynolds number based on the diameter is between 0.4 and 4, the value of C is going to be 0.989, okay, and M is going to be 0.33. Our next regime is between 4 and 40. And so if your Reynolds number falls within those ranges, then the C value is going to be 0.911. And the M value is going to be 0.385. The next regime is between 40 and 4,000. And so in that case, the C value is 0.683. And the M is 0.466. Right, the next regime is between 4,000 and 40,000. And so in that case, the C value is 0.193. The M is 0.6 618. Okay. All right, and the last regime we'll look at is between 40,000 and 400,000. So here, C value 0.027, and the M value is 0.805. Okay. Right. So it's a little bit of a more complicated case. Again, because the fluid mechanics is just a little bit more complicated in this case. Right? And so you're going to have to, use this correlation here, but also refer to the values in the table depending on what the Reynolds number is. All right. Let's see. And so if you notice, as the Reynolds number goes up, the value of C goes down, but the value of M goes up. Okay. And that matches kind of the same trends that we saw in the flat plate. So once we went turbulent, then the number in front, the coefficient in front, its value went down, but the exponent on the Reynolds number went up. All right, any questions on this before we do an example? Yeah. It's a D. Yeah. Yeah. So that's to refer to the fact that this is the Reynolds number based on the diameter of the cylinder. Okay. All right. So let's do an example just to kind of see it all in action. And the nice thing about this example is that this is a little bit more of a more classical case of the convection problem solving methodology. Okay, and so here we're going to have just a classical cylinder and cross. Okay. Remember, this is flow on the outside of the cylinder. All right, so here's our cylinder. Okay. We'll do a little bit different this time, and so instead of air, we're gonna run water at this. Okay, so our fluid here is going to be water, and it's going to have a U infinity of 0.1 meters per second, and the T infinity is going to be 12 degrees C. Okay. The diameter of this, cylinder is going to be 12 millimeters. Okay. And we also know the length of the cylinder as well. Okay. And so the length of the cylinder into the page is going to be 80 millimeters. Okay. And we also know the surface temperature. And so the temperature on the surface of the cylinder, this is going to be 50 degrees C. Okay. And so in this problem, we're interested in two things, but they are very closely related. And so once we compute the first thing, we can get the second one. Okay. And so in this problem, we're interested in computing what the average convection coefficient is and then once we compute the average convection coefficient, we can compute the rate of heat dissipation from the cylinder. Okay. So this is a more classical problem where we have, all the fluid properties, and what's unknown is going to be the convection coefficient. Okay. And so we can follow basically the recipe, from start to finish. And then by the end of that recipe, we'll have our convection coefficient. Okay, any questions on the setup for this example here? Okay, all right, so let's get into it then. And so first, or let me say convection recipe. All right, so step one of the recipe. Step one is to identify our geometry. So far, we only have two options. And so our first option is either a flat plate or it's either a cylinder and cross flow. And so you can see here that this one is a cylinder and cross flow. Okay, so let's go ahead and write that down. right, so next let's compute the film temperature. And so our film temperature is just the average between our fluid temperature and our surface one. Okay. And so we're going to take 12 degrees C, we're going to add it to 50 degrees C, divided by 2. And what we get from that is 31 degrees C. Okay. Right. And so now that we know the film temperature, we can go ahead and evaluate the fluid properties. And so in this case, we have water, and so that's different. Okay, and so make sure you know what fluid you're working with. Okay, so we're looking at the properties of water. And so if you're using the textbook, the properties of water are in table A6. Okay. But if you're using the online calculator, there's a water option there too. So make sure you just change it to for water on that on the website. Okay. And so the properties of water at 31 degrees C, what we have for this is the kinematic viscosity is equal to 7.73 times 10 to the minus 7 meters square second. Okay. The thermal conductivity is 0.62 watts per meter Kelvin. Okay. And the Prandtl number here is 5.20. So those are all properties that you would read just straight off the tables and or straight off the website. All right, so next thing we're going to compute is the Reynolds number. And since we're in a cylinder and cross flow, we're going to compute it based off the diameter, okay? And so it's tempting, and I've seen people do this. Whenever you have a cylinder, you know, we're almost always given the length of the cylinder into the page. Don't use that length for the Reynolds number. Remember, we're using the Reynolds number based on the diameter. Okay? So we're going to have U infinity multiplied by diameter divided by the kinematic viscosity. Okay. And so our velocity here is 0.1 meters per second. Our diameter is 12 millimeters. And then our kinematic viscosity is just given right above. And so if we plug all those in, we get a Reynolds number of 1552.4. So now that we know the Reynolds number, we can go ahead and check the table. And so for a cylinder and cross flow with a Reynolds number of about 1500, you know, that puts us into this kind of middle regime right here, okay? Right. And so since our Reynolds number is between 40 and 4000, what we can say is that the C value for this is going to be 0.683, and then our M is going to be 0.466. Okay. All right. Any questions? Any questions? Yeah. Yeah. So for the cylinder, you know, we have a little bit more granularity. So it's difficult to call it just laminar or turbulent. I would consider this pretty laminar because the Reynolds number is pretty low. But we have the wake region to consider as well. And so because of that wake, it kind of complicates things where you can't really say it's just laminar or turbulent. But usually I would consider these first three, you know, if I had to label it, I would consider these first three laminar. And the last two, I would consider those turbulent. Yeah. Mm-hmm. Okay. All right, step 4. So step 4 is to decide if we want local or average. Here it doesn't really matter because we only have one neutral correlation anyway. So we don't have a choice. And so we're going to pick average. Okay. All right, and then the final step is we're going to select our neutral correlation. And so we know because we're in cylinder and cross flow, our neutral number is going to be C times the Reynolds number based on the diameter to the M power times Prandtl number to the 1/3. Okay. We've already computed the Reynolds number, and so we can just plop that right into here. And from the table, we know the value of C, we know the value of M. Okay. And so we plug all that in, and we get a Newton's number of 36.32. Okay. We can then use this Newton's number to compute H bar, right? Because we know the definition of the Newton's number is equal to H bar. In this case, we're working with diameter, and so it's H bar times the diameter divided by the thermal conductivity. Okay. And from our correlation, we know the Newton's number in this case is 36.32. Okay. And so let's go ahead and solve this expression for H bar. And so we have H bar is equal to 36.32 times the thermal conductivity divided by the diameter. Okay. And so if we plug those values in, mostly because the diameter is so small, what we get is an H bar of 1876.53 watts per meter squared. And so that's part one of the problem. And so the part one of the problem is to find the convection coefficient, and we just followed our convection solving recipe to compute. Okay. And so again, this is a little bit more traditional in terms of what you can expect to see from a convection problem. Okay. And so I think problem 2 on the homework kind of follows the same process, but for a truck instead of a cylinder. Okay. All right. Any questions on how we obtain this result here? All right, and so now that we have the convection coefficient, let's go ahead and use that to find the other thing. Okay, and so remember the other thing that this problem asked us to find was the heat dissipated by the cylinder. Okay. And so, as always, whenever we're computing heat transfer in a convection situation, we're going to use Newton's law of cooling, right? And so, the heat dissipated is going to be H bar multiplied by A times the difference in temperature. Okay. We just computed H bar, and so we have H bar. Okay. We know Ts and we know T infinity. We can also compute A based on the geometry of the cylinder, okay? And so this A here is going to be the surface area of the cylinder. Okay. And so the surface area of a cylinder, the way we're going to compute it is we're going to take the perimeter of the circle and then we multiply by the length. Okay? And so this is going to be pi d times L, right? And so we plug all that in. We have our H, we have the diameter, we have the length. We know what pi is, at least up until the 5th decimal for myself. And so we plug all that in, and we get a heat dissipation rate of 0.645 watts. All right. Any questions on that example there? Yeah. You can consider it like that. The direction of heat is kind of just relative to whatever direction you put the arrow in. And so usually if you define the heat to go from the hot surface to the cold one, and so in this case would be like that. If you draw the arrows like that, then it would be positive. Yeah, so heat. I mean, for most of this class, we're considering heat as kind of like a scalar almost, and so the sign just kind of indicates which direction it's going to go. So it's either going to go one way or the other All right, question. So for step 4, why did I choose average and not local? In what case do we choose local? Yeah, good question. And so, you know, for most of this class, you know, we're going to choose the average Newsel number, because what the average allows us to do is it allows us to compute kind of heat transfer from an overall system. A local Newsel number will be useful if you want to compute the heat transfer from a specific point, right? And so if you want to compute the heat transfer from that specific point only, then that's when you would choose local. But for this class, you know, just because of the nature of the problems that we can do by hand, most of the time we're going to look at kind of thermal systems as a whole. And so, you know, practically speaking, you know, this is kind of beyond this class, but, you know, the only time where you're really interested in like a local Newsel number or a local convection coefficient are really only when you're doing simulations. And so if you're doing kind of a heat transfer simulation, then, you know, that's the only chance when you look at local, because otherwise it becomes, you know, a little bit too, the calculations become a little bit too heavy for kind of a normal person to do. Yeah. And so if you're going to be doing hand calculations, average is going to be what you're going to be looking at most of the time. All right, any other questions on this? Okay. All right, and so before we move on to internal convection, I did want to make a quick comment on one of the homework problems. And so this is going to be problem 3, okay? It's not about this problem specifically, but it's for situations like this, okay? And so, you know, let's look at situations when you have flow on both sides of a plate, okay? Because so far, you know, we've only considered flow on one side of a plate, right? But it could happen sometimes that if you have, you know, a plate that's, you know, very large, such that you can have different flow conditions on one side or the other, okay? And so let's say on the top side of this plate, okay, you have a certain velocity, you have a certain temperature, okay? And you have certain properties up here, okay? And so you have a certain thermal conductivity, a certain viscosity, a certain Prandtl number, okay? But maybe this glass, you know, in this case, we'll assume that it's a glass, okay? It's separating you from a very different condition on the other side, okay? And so on the other side, you might have totally different flow conditions. The flows don't necessarily have to go in different directions, but I drew them as different directions here just to kind of emphasize it. Okay. And so I think in the homework, the situation I'm having you look at is a car defroster, okay? And so if you've ever, I mean, nowadays it's more common. So if you get into your car kind of early in the morning, you know, you can't see out of your car because it's all frosted up. And so, you know, in order to fix that, you know, you turn on your defroster, and, you know, which kind of involves turning on the AC or the heater inside your car. And so what you're going to have is a very different kind of thermal condition on one side versus the other. But on both sides, you might have some airflow. Okay. Another situation that I just thought of now, you know, just because I've been wanting to go to the aquarium for a while, is that, you know, this can be used to model, you know, maybe the glass that separates you from like the shark on the other side of an aquarium, right? And so the shark is going to see a very different kind of flow situation, right? And so they have water that's flowing, but on your side you have air, okay? And so that's kind of another example of something I can show you. Okay. And so in these situations, you know, what we assume most of the time is that the plate here, or the separating surface, has kind of a negligible thickness. Okay? Okay. And so in other words, the solid plate here is not going to contribute thermally, to the situation at all. Okay. And so for these situations, what you can have, what's going to happen is that you almost have like a direct transfer of heat from one fluid to the other. Okay. All right. And so, let's say, for instance, that T infinity 2 is greater. Okay. And so what you're going to have is kind of a net transfer of heat that comes out from the bottom fluid and goes into the top one. Okay. And so if the plate isn't thick enough to contribute thermally, what you have is Q convection 2, okay, where Q convection 2 represents the amount of heat that's leaving the second fluid. This has to be equal to Q convection 1, right? And so that's the amount of heat that's being gained by the other fluid through convection. And so if we substitute Newton's law of cooling into this, okay, then we get the following. And so if we have on the left side here, we have H1 bar multiplied by the area times Ts minus T infinity 1. Okay. This has to be equal to H2 bar times A times Ts, or excuse me, since we're assuming T infinity 2 is greater. And so this can be equal to T infinity 2 minus Ts. Okay. And since these two fluids are interacting through the same plate, the areas are going to be the same, and so we can cross out the areas, okay? And we end up with the following expression right here. Okay? And so in these types of problems, you're going to basically set the two convection heat transfers from the two fluids directly equal to each other. Okay. Right, where Ts is the temperature of the separating surface. And so if I can go back up to this diagram here, okay, we assume that the plate has a temperature of Ts. Okay? So Ts is kind of like the in-between temperature in between the two fluids. All right, and so if you have that set up, then you should be in good shape for that homework problem. Okay, and the funny thing is, the first time I did that problem, when I had the incorrect answer, the solution wasn't that reasonable, but it was at least realistic. Now that I've corrected my solution, the situation is not so realistic, and so just keep that in mind. So you're going to get a temperature for the inside of your car that is not physically possible, but just kind of keep that in mind. Okay. Okay. Any questions on any of this? Okay. So we have 4 minutes left, and so let me just kind of introduce the idea of internal convection, and then we'll really kind of get into it next week. Right. At the very least, what I want to communicate to you is what makes internal convection different from external convection. Okay. Okay. And so when I mention internal convection, these are situations when you have flow that's kind of on the inside of two bounded surfaces. At least two bounded surfaces. Right. So normally what we have here is we have our our free stream conditions, okay? And so we have our fluid with the velocity u infinity, temperature T infinity. Okay. Right. And before, what we said was that this, this flow is striking this flat plate, okay? And it was striking it in such a way that the boundary layer on this plate can kind of grow unimpeded, okay? So this was external convection. For internal convection, we're going to put another surface on the other side. Okay? And so that's what I mean when I said that the two surfaces are bounding. Okay? And so they bound the flow in between them. Okay? And so what's going to happen here is that once the flow kind of hits the, we'll call it the ceiling here, okay? A boundary layer is going to flow on that as well, form on that as well. Okay? Right. And so the important difference, let me just kind of redraw this a little bit. Okay. The important difference is that if you look at the boundary layers from the bottom and the top, eventually they're going to meet. Okay. And it'll meet in such a way that, the entire internal flow will be inside the boundary layer, okay? And so why is this important? Okay. Remember, the boundary layer was kind of the transition region between the surface conditions and the free stream, right? But if our two boundary layers meet, and we look at the flow kind of on this area over here, right, on the right, we've lost all sense of the free stream. And so we've kind of forgotten what U infinity and T infinity is. Okay. Okay. And so that kind of shifts our, how we think of these kinds of problems. So instead of thinking of, them as the surface versus the free stream, we're going to have to kind of reform how we're thinking. And in fact, we have two different regions here. At first we have this region, before the boundary layers meet. We call this the entrance region. Okay. And then once the boundary layers meet, then we have, this other region, which we call the fully developed region. And for this class, we're going to focus most of our attention on this fully developed region, just because the fluid mechanics and the thermal stuff is a little bit easier there than the entrance region. Okay. So any final questions on this before we wrap it up for the week? Okay. All right. So that's all we got time for. And so next week, we'll really dive into this stuff. Okay. But you should have everything that you need for homework 4. So homework 4 only covers external convection. So you should be able to do all the problems on them now. And remember that homework is due next Friday. All right, so I hope everyone has a good weekend. Thank you guys for tuning in today. And I'll see you guys next week. Well, if you haven't picked up your exam, I have them here. So I think I have only just 5 left here. So if you haven't picked them up, then you can come pick it up. Oh, cheat sheets I think are in my office. So I forgot to bring them. I'll bring them.
I can pick them up another time.
Okay, yeah, just come to my office and I'll help.
Thanks.
Okay, yeah, go for it. Hey, how's it going? Okay, yeah, sure. Should have about 410. Yeah, 410. So 315 is the machine shop. Dr. Lisi. I don't see why we wouldn't, because it is a popular class. And so, and this year we did something different. We offered it. Usually it's offered in the spring. What I've been seeing is that a lot of people use it for like their senior design class, or they're part of like rock hyper rocket, or like the and so what we tried this semester is we put it in fall so that you can learn all the ANSYS skills that apply it. So it seemed to go pretty well. So I don't see why we wouldn't be able to offer it in the fall.
I was just worried that it'd be
It used to be, but I think now we're going to turn it to fall. Nice. Oh, it is that point. I kind of drew it forward. It is the point when they two actually. Yeah, yeah.